In Unit 5, we only made conclusions about, or all of the probabilities we found were probabilities of discrete variables. And when I say discrete, like my unknown was how many successes occurred, right? Whether it be in a time frame or how many successes occurred in a set number of trials. Okay, so continuous variables. So Unit 5 was all about discrete variables with probability attached. Unit 6 is going to be all about continuous variables, okay? So imagine, we can actually see the grass right now. Imagine we were to go outside, everybody with a ruler, and we all go out and measure the lengths of several blades of grass. Is anybody going to get a blade of grass that's exactly 4 inches tall? It would be pretty spectacular to find a blade of grass that is 4.0000000 inches tall. Okay? Because like depending on how precise we want to measure, nothing's exactly, right? Okay? All right? And so as we think through what might it look like if most of the grass, like I'm thinking about my own backyard, so you guys, my yard has fences on both sides, and so the south side of my backyard is almost always in the shade, and the north side of my backyard is almost always in the sun. So the north side grows much taller. And in fact, most of my backyard grows tall, and then some of my backyard doesn't grow at all. Does that make sense? Okay. So if we were to make a dot plot of the grass in my backyard, we'd have a whole bunch of big values with a few low ones. And that would be each of us goes and measures a piece of grass out of my backyard. Okay. If my yard is freshly mowed, they'll all be the same height. Right? Okay. So now, if I draw this picture, again, mostly really tall grass in the summertime, and then, that one like patchy area that doesn't get much sun stays pretty low. If I want to know, say, what's the probability of lower, I'm almost like adding up an entire area. So like in discrete variables, we could find exact probabilities and add them together. In continuous variables, you can't find exact probabilities, so you're kind of looking at a whole area underneath a graph, okay? So what I have here is an attempt at a kind of like a smoothed out curve over top of the lengths of grass in my backyard, okay? And so if I want to know what is the probability a randomly selected piece of grass is less than 4 inches, I might find what I'm saying is, what is this area? Oh, that didn't go well at all. What is this area that is less than 4 inches? And if I look at this picture, in reality, there's not a huge difference between less than 4 and less than or equal to 4. Because, in fact, equal to 4 is pretty unlikely. Is everybody okay? All right, now, if this graph is representing 100% underneath of my grass, the area underneath this graph, this is a special graph we call a density curve, the area underneath it is always 1. 100% of the grass is going to fit on whatever picture I have of my distribution. Is everybody good? And so with discrete variables, we're adding up probabilities. With continuous variables, we find area. Okay, we're finding the area underneath the graph. What are you guys studying in calculus right now? Have you done anything with area yet? We will not be doing any integrals to find the area underneath this curve. Your calculator has pre-programmed to do the area that we need it to do. So you guys don't need to worry about having to integrate any functions in this class. Okay? All right, so let's turn the page. All right, so there's kind of two different, in the same way in discrete distributions, we talked about just a given discrete probability distribution that isn't necessarily binomial or Poisson, but could be given to you, right? Like that, the very first question on your homework, I gave you the probability of each outcome, okay? Likewise, there's more than one continuous. We're going to focus on two of them. The two we're going to focus on is the uniform distribution, which is relatively easy to do, okay? And then we'll also do the normal distribution, which also is easy, just not as easy as you guys think. Not as easy as what we've done so far with the normal distribution. We'll have a little bit more to it. Okay, so let's draw a picture of this one. So uniformly distributed means you have as many like 12-foot trees as 13-foot trees, as 14-foot trees, and in between, okay? So if I'm saying the trees are uniformly distributed between 12 and 17, that means if I were to say draw a bar graph, each of the bars would be approximately the same height. So this bar and this bar and this bar and this bar and this bar are all the same. All right, and if I tell you that underneath this is 100%, how much is each one? 20%. Now, because these are all the same, we can just kind of add stuff together. Okay, so if I ask you what is the probability x is less than 14, I can shade less than 14 and I can say what area have I shaded? And the answer is 40%. No problem. Now, what if I asked side probability? The probability x is between, so I'm going to do like negative 13.5 and 15.5. So if I shade that, that would be roughly this. What area is that? It's also 40%. Because we could look at it as like, oh, this is 0.1 and then 0.2 and then another 0.1. We see it? Okay. All right, fine. I'm going to do one more. 13.2 is this the and 15.75. Now how are we feeling? Seems slightly more annoying, right? And in fact, I could do 13.23 to 17. Okay, so it'd be nice with these uniform variables if there's a formula to follow, because we don't have to worry about the height influencing the probability, because since it's all equally the same height, okay, what we can do is the length of the interval over the total length of the interval, the length of the desired interval over the length of the total interval. So if I was doing that for this one, I might do 15.75 minus 13.2 over my total of 17 minus 12. It tells me what percentage of the number line my range takes up, and since they're all the same height and equally likely, it's not a problem to just look at those lengths. So, does that make sense? So let's see. That would be 2.55 over 5. Does that feel about right? So I think 0.51. Are we feeling good? All right, now, before we do this one, I want to point something out, that this is, what we have is food package delivery times are uniformly distributed between 3 p.m. and 4:30 p.m. So I could look at that and immediately say, oh, this is Poisson, right? Because Poisson is the one that was over a time period. Okay, and at the very first sentence of this could be Poisson. However, What is the probability that a package will arrive after 4:14? I want to find the probability X is bigger than a certain amount of minutes. Do you guys see what I'm saying? I'm like, essentially, I'm trying that my X in this case is not a number of successes. It is another time frame in which this package would be delivered. Did you guys see what I'm saying there? Okay, so what that X stands for could help you decide, is it Poisson versus is it binomial? Is it, say, this uniform distribution that we have to use? Now, we're still going to do desired interval. So that would be 4:30 minus 4:14 and 4:30 minus 3 o'clock. But keeping in mind, what we're really doing is subtracting minutes here, yeah? Okay, how many minutes between 4:30 and 4:14? 16 minutes. How many between 4:30 and 3 o'clock? So 16 of the 90 minutes. What's the probability it lands in those 16 of the 90 total minutes? How are we feeling, okay? And then from there, you get what you get. I think it's like 18% if I'm doing this from memory. 17.7% or 17.8%. Okay. Are we feeling okay? All right, why don't you guys try this one for me real quick? We'll make sure we're good on this, and then we'll move on. We all feeling really good? Okay. Next, let's turn the page. This is where we're really going to need our calculators. That's annoying. I think that will do what I need to do. Have you guys see what's going on here? All right. Okay, so the standard normal distribution. Okay, when we say standard means a normal distribution of z-scores. Okay? Because z-scores are what we do to standardize and compare different things. Okay, so they're the standardized score that takes into account the size and the spread of a distribution. Okay? A reminder that the z-scores, in general, the interpretation of a z-score is how many standard deviations above or below the mean any one observation is. So, if I think that through and I say, what is the mean of the z-scores? Z is your number of standard deviations from the mean. So the z-score that goes with the mean, well, how many standard deviations from the mean is the mean? 0. So the mean of z-scores is always 0. And the standard deviation of z-scores is always, well, if something's one standard deviation away above the mean, its z-score should correlate with the number 1. So whenever we're talking about z-scores always have a mean of 0 and a standard deviation of 1. Is everybody with me so far? Okay. Now, normal distributions are also continuous. So what we'll want to do is find the area between two things, okay? So if I'm going to go ahead and draw in my lines, by the way, this should be from -1 to +1. Both of these should be positive. I don't know why they are not, okay? So what is the area between -1 and +1? That's like saying what percent of my values are within one standard deviation of my mean. Does anybody remember what that was approximately for normals? 68%. So we would anticipate that the probability of my z-score being between -1 standard deviation and 1 standard deviation from my mean would be about 0.68. Does anybody remember what 2 standard deviations should look like? 68, 95%, 0.95. And if I kept asking you questions that were like a whole number of standard deviations away, this would be really easy. We wouldn't need our calculators. But now I'm going to ask, what's the probability I get a z-score below -1.45, and that starts to feel real icky, okay? So it turns out that normal distributions like the binomial and the Poisson distribution are predictable and programmable distributions. So if I want to do something with the normal distribution, I better find where are my known predictable distributions in my calculator. Is everybody with me? So let's go ahead and say, well, where do I find my known predictable distributions? I hit second bars. Which one? I see 3 different ones for the normal. Here's the deal. The PDF only tells me the height of that bell curve at one spot. We're never finding just one spot, right? We're finding areas. So we're going to choose the CDF. So choose normal CDF. And we're going to actually do this one so you guys can see it, okay? So rule of thumb is if you have to communicate it to the calculator, I want you to communicate it to me. So far, the only thing we've done to communicate this to the calculator is picked the normal curve. You're going to communicate that by drawing the normal curve for me. I will expect to see graphs drawn for these. Okay? What I'll need on that graph are the mean and the standard deviation labeled. Right now it's going to feel silly that you need to do that. Eventually it will not. And then what I'd like you to do, since we know, I want you to communicate to me that you know that you find probability by finding area, by shading the area we need to find. So if I'm doing from -1 to 1, I'm going to shade the region in between -1 and 1. All right. So what your calculator is asking for, that when it says lower and upper, it is looking for the boundaries of what you've shaded, okay? So the lower and the upper describe the shading on your picture. In this case, my lower is going to be -1, the left boundary. My upper is going to be +1. When it's that's supposed to look like that next symbol where it says 0 and 1 automatically, that's supposed to be that mean, the population mean of 0 and standard deviation of 1. It should be pre-programmed in yours. That's where it should start. Okay, if not, put in 0 and 1. You're going to go down and hit paste, hit enter, and lo and behold, we got about 68%. Is everybody good? So if I were going to do this next one, shading in that center. Okay. Okay, again, what are we expecting here? In my calculator, I'm going to put my lower to be -2, my upper to be +2. I would expect my answer to be pretty darn close to 95%. And lo and behold, 0.954. All right, so now what do we do for this one? So let's draw this picture. What's tricky about this one is, what is my lower boundary of my shading? Yes, but it's a great answer, but no. It shows that you understand that normal distributions typically go 3 in each direction, but it doesn't go, that's 99.7. Okay? That's not 100%. Okay? So what we're going to do, and even then, that 99.7 is an approximation. Okay? And when we start applying this outside of the normal curve, it's going to make we're going to have huger standard deviation. We've got to think through it a little bit, okay? So what we're going to do is we're going to call this, and it is technically negative infinity. Now, does anybody know where the infinity button is on your calculator? Neither do I. There isn't one, okay? So what we do is we use negative a gajillion, just a negative a lot of, a really extreme, high magnitude negative direction number. So you guys with me? So my lower boundary will be negative, and then I just hit 0 a bunch of times. Because what the calculator does is it finds the area to the left of your first value, or of your upper, minus the area to the left of your lower. So as long as you use that negative a gajillion, the area to that left is so tiny it doesn't really matter. Before I hit enter, what kind of number are we expecting? Small, really, really small? What are you thinking? Pretty small? Like, what is pretty small? Like 0%? 2%? 8%? 20%? You want to know what I know for sure? That my answer will be between 16% and 2.5%. Because if I got 68, right, that half is 34. So it's one standard deviation away has 16% below it. 2 standard deviations below has 2.5% below it, give or take. Give or take. You guys see what I'm saying here? Okay, so the reason I'm pointing this out is understanding what our answer means is really important. Should I be upset if I get a negative number? I should be very upset if I get, because the area cannot be negative. Yeah.
Would it be negative 1.44 because it's not equals to?
Ooh, but you know what is? 1.49999999999, so 1.4 doesn't work. Okay, so, but Jeremy, equal to does not, strictly less than or equal to does not matter with continuous, because the probability that it equals exactly 1.45 is
right.
Cool?
Yeah.
And there we go. We can see that it's in between. It's just that runs to that, yeah. It is in between 2.5% and 16%, right? Where it is in between there is impossible to figure out, but okay. All right, so let's draw this next picture. Again, notice every single time, even though I could just punch these in without drawing a picture, I'm not, because my expectation is that I see this picture. I have a recording of me telling you that I'm telling you to draw the picture. So if you don't draw the picture and get mad, I'm probably going to play this recording for you. Are we good? Hey, just looking at the picture, what do we expect our answer to be? 60% is a great guess, right? Like a little bit more than half. Can we at least see from the picture why this is a little bit more than half? Again, guys, I'm not trying to, this is not me talking down to you. It's me understanding where students struggle on this. Like making sense of your answer is really important. Okay? Every good? What are we getting? So let's see, what would we do here? What would be my lower? Negative 0.2. My upper? A gajillion. Some really big number. Oh, man. Poor Tatum. She's watching this video. She's not watching it right now, but when it will be present tense for her when she watches the video, and the calculator's like off screen for half of it. Oh, look, it's pretty darn close. I was 60%. It's a pretty good guess. Because that would round to 0.579. Why don't you guys do this last one for me? Make sure, draw the picture, do everything. We'll make sure you're meeting every expectation I need from you. How we doing? We good? We feel good so far? Okay, great. Let's turn. All right, y'all. What is the z-score of the 35th percentile? Whew. I feel like I don't know how to do this without at least like drawing a picture of seeing what this even means. Yeah? So let's think this through. Can somebody remind me what a percentile is? What does it mean if I say my height is the 35th percentile, besides being overly optimistic about my height?
You're 15% shorter than most.
Hold.
You're 65% shorter.
I am shorter than 65% of people.
Yeah.
Another way of saying that is
You're taller than
my height is bigger than 35% of people. Again, incredibly optimistic, I know. Okay? But hold on. How would that apply to the normal distribution?
Oh, okay, well, I wasn't thinking about that.
Because that percent of people... So could we draw a line on our normal curve where the 35th percentile would be approximately? Would it be on the left or to the right? We're good with that? Okay, so let's see. I'm going to just tell me when to stop, where you think I've hit about 35%. Right there? Nah? Nah?
Stop.
We all feel decent?
A little less, maybe.
I think maybe a little less. Right here?
Yeah.
Is this okay?
Well, nice.
How about right there?
Yeah.
Give or take? I appreciate you being willing to take the risk of answering, Mario. Can you tell me how you made that decision? Like, when I say 35%, 35% of what?
100.
100? The whole graph. And what about the area of that graph? Yeah? Okay, so when we talk about that percentage, what we're saying is I don't know the boundary, but I know that this area is 35% of it. So, thinking through the process we've been doing with our upper and our lower, well, I guess I know my lower is negative a gajillion. Do I know my upper? No, in fact, I know the area instead, so I have to work backwards. You guys, does anybody remember the mathematics word for backwards operations? What do we call them? Inverse operations, yeah? So let's go back into that menu real quick. If I go into second vars and I do this one more time, do I see anything that might help me work backwards or do the inverse operation for the normal curve? You guys, I'm not trying to talk like you're 5-year-olds, but it is built with there's a process behind how the calculator is built. So if I choose that inverse norm, it asks me for an area. And then it says left, center, and right. Does anybody's calculator not say left, center, right? Perfect. Okay, so what I need to tell it is that I know that my left-hand area is 0.35 if I hit enter. Now, no, before I hit this, you guys, it's going to give me this number. Can somebody tell me what we know about this number? Anything.
Less than 0.
It's going to be less than 0. Is it okay to get a negative here? Sure. Because all that negative tells me is I'm finding a boundary that is below the mean. Is everybody good? So I go ahead and I hit enter. I find that z-score is negative 0.385. Now, big picture, what I need you guys to get from that is that for any normal distribution, in order to be the 35th percentile, that person, whoever that is also 0.385 standard deviations below the mean. Everybody good? So we talked about percentile and z-score as measures of position. They're describing where things are. It makes sense that someone below the mean would have a negative z-score. 35th percentile is not super low, so not a lot of standard deviations below the mean. We feeling okay? Cool. This is a good stopping point. We'll start up with these 2 examples tomorrow.